All right, here we go with day number 3, Euler's method for finding y. Let's go ahead and get started. All right, here's an example of a separable differential equation. I'd like you to solve for y. I'll come back with, let's see, I'm going to separate and integrate, and I'll start the initial condition portion. I'll come back. All right, so I separated and brought this y squared over as 1 over y squared. Left the x cubed over 5 over here. Integrated, got negative 1 over y equals x to the 4th over 20 plus c. Now I'm going to place that initial condition in there to find that constant on the end. This right here, negative 1 over 2, is the same as negative 10 over 20. It's equal to 1 over 20 plus c. Therefore, it looks like c would be negative 11/20. So I'm going to place that back into this step right here, and I'm going to solve for y. So I get negative 1 over y is equal to, I'm going to go x to the 4th minus 11 all over 20. All right, now I'm going to change the sign here. That would just change the 11 to positive, the x to the 4th to a negative, still over 20. And then I'm going to take the reciprocal, which would give me that. There is our function whose derivative can be represented by dy dx with the initial condition 1, 2. All right, let's get started with Euler's method. All right, so this is a fancy drawing here. I'm going to draw a new one, and I'm going to show you exactly what's going on here. All we're trying to do is estimate a value of y. So let's say I have some function, and I don't know what the function is. I don't know what that function is, but I do know that its derivative is 2x. Okay, so let's say I know one point. One point is 1, 1. And I'm trying to figure out or get as close as I can to another point, 3, comma, question mark. And I want to get as close as I can to that. Okay, I want to estimate what that question mark would be using derivatives. Well, one thing we can do is, if we know this point here, 1, 1, we know the derivative at 1, 1. Therefore, let's take dy dx at this point 1, 1 and see what it equals. Of course, dy dx is only in terms of x, therefore I'm only going to employ this 1 right here. So dy dx would be 2 times whatever the x value is there, which would be 2. Okay, so the slope here, tangent to the curve through 1, 1, would look like that. Right, it would have a slope of 2. dy dx equals 2. Okay, I want to kind of backtrack just a tiny bit. But if I did that over this interval from 1 to 3, I could find a y value. It'd be an estimate, right? I could find that y value right there, and that would be what I could call an estimation of what this question mark would be. Now, the error would be significant, right? It'd be that far off. But how would I find that y value? Well, let me zoom in on that for a moment. Okay, and this is not to scale, so don't judge. Okay, but this right here, the blue line represents our slope of 2. This is going to be our change in y. This is going to be our change in x. Well, we know our change in x is 2. We know our change in x is 2. And for the purposes of my formula in a couple minutes, I'm going to call that h. Okay? So if I know that the slope of the line, change in y over change in x, is equal to 2 over 1, right? We determine that right here. Then I can find the change in y. Okay, change in y over change in x. So what I'm going to do then is I know that my change in x is 2, right, given right here. So I can find my change in y. So I'm going to multiply, I'm going to multiply, cross multiply, and I get 4 equals delta y. Therefore, this change was 4. So what would this point, or this estimate be? Well, it'd be 3, right, because we went 2 units. And it'd be a change in 4, so we would have to add 4 to 1, which would be 5. Now, the function that I gave you here was y equals x squared, and you might have been thinking that the whole time. What would the actual value be there? It'd be 9, so it's off by a pretty significant amount. Okay? So let's just talk through what we just did. We took dy dx, evaluated at our point, our initial point, right? X, let's go x sub n, y sub n. We took that and we multiplied it. What did we multiply it by? Well, we multiplied it by this change in x, right, our h value. This right here is really h, or change in x. This right here is going to be dy dx. So we multiplied dy dx times h, and then we added it, right? We added it to the previous y value. Right, our previous y value in this case was this 1 right here. And that gave us our next y value. Now, if you think about this, is there a way that we could make this more accurate? And the answer to that is absolutely, right? Let's say I know this point in between here is 2, and I don't know the value, but I know that's a 2. Well, what I could have done is I could have cut this into multiple intervals and just taken this original slope, the blue slope, up to the point where x equals 2, and then found dy dx here, and I could have found a much more accurate or closer, smaller error, right? But I could have found a much more accurate value for y there. And so then the iterations begin. How could I make the perfect fit, right? Well, then I change delta x to a very, very small number. So the more iterations you do, the closer you'll be to that estimate. So I'm going to use this formula right here on the pages that follow in order to estimate what y values would be using derivatives. So scratch this formula here. It's kind of written in a different way than how I want you to visualize it. Let's visualize this now for a second. Dy dx at some x value where we're starting times h plus y sub n where we started will give us the next one. Okay, so I'm going to make a table in a moment here, and we're going to start at a very specific point. So it looks like we start at the point 2,5. Okay, so our first point is 2,5. Our first thing we need to do is calculate the derivative at 2,5. Okay, so I'm going to fill out this first row here. And it looks like h is going to be 0.2, and what we want to do is we want to get to 2.6. So let me fill out a portion of this table here real quick. So our next value here will be 2.2, and we'll get a y value. Then 2.4, and we'll get a y value. And then we'll end up at 2.6, and that'll be our estimate. Okay? So if you would, go ahead with me and calculate dy dx of the 0.25, multiply by h. H in this case is going to be 0.2 in all cases, and add to y sub n. Y sub n in the first case will be 5. In the second case, it'll be whatever we get for our next one, and you'll see the iteration begin. All right, so when I plugged in 2 into dy dx and 5 into the y values there, I got a negative 3. Negative 3 times our h value of 0.2 was negative 0.6, added to 5, got 4.4. So now our next y value is 4.4. Okay, so let's recalculate using the same process again. Find dy dx with x and y plugged in, multiply by 0.2, and this time add to 4.4. We'll get a new y value. Okay, dy dx for me that time was negative 1.2. Multiply that by 0.2, add to 4.4, and I get 4.16. 4.16. So my next y value would be 4.16. I want to make a point here and coordinate these colors to show you that this just becomes the next y value that we use in this method. Okay, so we have one more calculation to do, and then we'll have our answer here. Let's find out what that value would be by going through the process yet again. All right, so I do this one more time. Derivative with respect to x, dy dx, the slope would be this, times 0.2 plus 4.16 equals 3.936. So it looks like my estimate in this case would be for 2.6 for x would be a 3.936. Now what I'd like to bring to your attention is how do I know whether or not this is an overestimate or an underestimate? Okay, so overestimates and underestimates have to do with concavity, which is the second derivative. Okay, and we're not going to get too far in depth here, but if the function is concave down, right, and let's say we start at this point and we start projecting slopes, right, and I go from my first point, x1, and I want to get an estimate of x2, right, that looks like that would be an overestimate. So if you have concave down, Euler is going to give you an overestimate. Okay, if you have a function that's concave up, right, and I go from x1 to x2, and I start projecting my slopes at whatever number of intervals you have, your estimate will be an underestimate. So if it's concave up, then Euler gives an underestimate. All right, cool. Let's look at one more example and we'll call it a day. All right, here in number 1, it says using a step size of 0.5, use Euler's method to approximate a value when x is equal to 2. All right, so if I know a given point is 0, 0, then that's going to mean I'll have 4 subintervals. Right, so that would mean you'd have to do the same thing I did on the previous page 4 times, just like we did. Let's look at this one. If I want to go from this point 0, 0.5, and I want to travel to 1, I don't know, on step size of 0.2, so h equals 0.2. Looks like I got to do it 5 times. So same process. Let's see here, same thing here, we do 0.5 as well. So let's go ahead and jump into this one. Okay, so it looks like the initial condition that's given is the point 0, 0.5. So I know 0, 0.5 is my first point. I'm going to go ahead and do the first round, but let's just lay out our other points. Let's see here. Step size of 0.2, I got to do it 5 times. And one more time. That'll be our final destination. This will be 1, we don't know. This will be 0.2, 0.4, 0.6. Uh-oh, I miscalculated. This will be 0.8. Ugh, gross. We got to do it that many times. All right, that's fair. Got to do what you got to do. All right, so why don't you go ahead and try the first 3 rows, see how far you can get and see if you can get it. Let's go round. I'm guessing it's going to be a lot of decimal work. Round to 3 decimal places. Let's go 3 decimals. All right, so it looks like I didn't obey my own rules and I went out to 4 decimal places. But I just want you to notice, like, you get this 0.65 and 0.65, then you use it to find dy dx, and you add whatever you get for that interval plus that, and you get this new value, right? Then you use that to find dy dx, multiply by 0.2, add it to itself, and it's just this repetitive nature of that, right? So I'm going to use this 1.7059, and I can use the calculator to my advantage. Okay, I get this 4.616 because the calculator saves, and you can just kind of repetitively do this. You get into a rhythm, and it starts to make a little bit more convenient, obviously more than a scientific calculator. So I'm going to take that times 0.2 and add it to 1.7059, and it looks like I get 2.6291. So it looks like an estimate for the output for x equals 1 on this function that's unknown ends up being 2.6291. All right, guys, that's Euler's method. If you wanted to, you could take the derivative of dy dx, and you could go ahead and determine whether it be concave up or concave down. That would be a good way to determine if it's an overestimate or underestimate. But typically within a problem, it'll say, it's strictly increasing, which would mean you'd be able to determine whether it's concave up or concave down, or tell you something about the second derivative. So, all right, there you go. That's it on Euler's method, and we'll see you next time.